So great to be here again and to see this growth since the last year. Now we have a bigger venue, 2 days instead of 1 day. So great developments. So again, very happy to be here. So today I'm going to talk about some work we are doing at Berkeley at RISELab. And let me start with a few words about RISELab. So what do we do in the RISELab? So we study the design of real-time, intelligent, secure, and explainable algorithms and systems. And why is that? Because these algorithms you are seeing more and more in a variety of application domains, such as fraud detection, robotic surgery, financial analysis, self-driving cars, IoT, and many more. And when we are talking about these kinds of attributes, real-time, intelligent, secure, explainable, just to quantify them, when we are talking about real-time, we are talking about algorithms and systems which can respond in milliseconds, sometimes faster. Intelligent means obviously it's using sophisticated models and algorithms. Secure is about protecting both the data, the systems, and the models. And explainable is basically about auditability and verifiability of the algorithms. And this effort, it's an interdisciplinary effort, bringing together people from AI, security, hardware, and systems, and we collaborate with a group of great partners and sponsors. So now, in this talk, I am going to discuss and cover a subset of research we are doing in RISELab, and it's about systems and ML. And how is, it's customary by now when we are talking about system and ML, we are talking both about system for machine learning and machine learning for systems. So I'm going to talk about 5 projects, 2 under system for ML, Ray and Helen, and 3 in the category of machine learning for systems, how to use machine learning to improve systems. Deep queries, NeuroCats, and Autopandas. So let me start with the system for ML first. And I'm going to start here with stating 2 trends everyone is aware of. One is more and more applications are becoming distributed. And this is driven by 2 things. On one hand, the amount of data we want to process is still growing exponentially. And as you may have seen and read, the model size also increases exponentially. This is a plot from OpenAI. And this shows what is the largest model, size versus time. And according to this blog, that doubles every 3.5 months. Okay? So much faster than the Moore's law. And on the other hand, as we know, the Moore's law and Dennard scaling have ended. They are dead, right? Now you get just a very low, in low percentages improvements year over the year in the performance of one core. This is a Moore's law. And basically, the Dennard scaling, what it's saying is that it used to be that in the same area of silicon, if you cram more transistors, the power which is dissipated or you need for that area remains constant. Right? So as the number of transistors increases exponentially, you are going to have exponentially more power, more memory. Of course, there are a lot of efforts in building specialized hardware to account for this Moore's law end. And if you look about NVIDIA, they have the plots in which the performance of their chip still doubles every 18 months, like Moore's law. So this will continue for a while. However, this will not happen for the memory, right? The DRAM, it's about the number of transistors you can cram on the chip. And again, because they are scaling, you can no longer cram, put the same number, to increase exponentially this number of transistors. So the memory itself will be a limitation. And because of that, this alone will lead to having this, to more and more, to forcing you to distribute the programs. If you want to process exponentially more data, to run exponentially larger models. Right? And the second trend is obviously, that's why we are here, more and more applications are leveraging AI. right? In one form or another. So this brings me to the first system we developed. We started developing it almost 2.5 years, 3 years ago. It's called Ray. And the problem it tries to solve is to deal with the ever-increasing complex machine learning ecosystem. And today, if you want to build an end-to-end application, AI application, you need to do some data processing, to do featureization, maybe data augmentation. You need to do, then obviously, you are going to do training. You are going to tune the models using hyperparameter search. Then you are going to need to self the models. And if you are going to do some reinforcement learning algorithms, likely you are also going to do some simulations. And today you have many of these, almost in any of these systems, now you have distributed system offering, right? And you have for training Horovod and distributed TensorFlow, model serving TensorFlow and TensorFlow serving and Clipper, and so forth, okay? So the point here is that if you want to build an end-to-end AI applications, you need to stitch together all these kind of tools, and that's difficult. Time-consuming, it takes time to convert from the format required by one framework to another, and so forth. So Ray tries to solve that problem by providing a general-purpose distributed computing framework for Python and now Java. And on top of that, you can implement this functionality as libraries, right? So the promise here is that you can implement all your end-to-end application on top of Ray. At the core of Ray, we have a dynamic task graph backend. And think about this, and I'm not going to go into much details, ability to execute millions of tasks per second in a dynamic, which are organized in a dynamic task graph, and also provide fault tolerance. And Ray will provide you two APIs, pretty low-level APIs, Task Parallel API and Actor API. Okay? So why is Ray general? One way to explain this is that if you think about, in most programming languages, you have two constructs. On one hand, you have functions. On the other hand, you have classes, objects. So what Ray is doing is transparently takes the functions and these objects, and they can execute them remotely and in parallel. That's what it's doing. So on the left-hand side here, you have a function which reads two arrays from two files and adds them up. And on the right-hand side, you have a class, a counter class. We just incremented a counter, right? So Ray, again, can take these two constructs and transparently execute them remotely and in parallel. And to do that, you just need to add some simple decorators to the functions or the classes which you want to instantiate remotely. And when you invoke the function, when you run that function, you call that function, or you invoke a method of a class, of a remote class, you also need to add the remote decorator. There is one thing happening here is that when you call a remote function or a remote method, what you get back, you don't get the value returned by that function. What you get is an identifier or a future. And here is just a very simple example to see what happens under the hood for when we parallelize a function. So assume here the two files, input files, are on two different machines. So now when you execute the first instruction to read the array from file 1, what happens is that Ray will automatically spin off a task on the node which stores the input to read that file. Now, the main point here is that this call returns immediately. Again, doesn't wait for the function to get executed. It returns a future, an identifier. So therefore, the program, the driver, can go ahead and launch the second task to read the second file, and then the third one to make the addition. So at this point, for instance, all the tasks are launched. Actually, some of them may not even have started execution. And under the hood, Ray will take this dynamic task graph and try to schedule it so that to exploit the parallelism. In this case, the parallelism will be, for instance, the two reads arrays for file 1 and file 2. They have no dependencies. They can be executed in parallel. And finally, when you want actual result, you have to call this array get. And this is a blocking call, and it waits until all this dynamic task graph is evaluated, and the results is going to be provided to you. So that's basically what it is at the high level. Now, this is pretty low level API, but it's very powerful. On top of it, we built a few libraries, and two of them I'm going to talk about very briefly. It's a library for reinforcement learning, and another one for hyperparameter tuning. So first, RISELab, our library for reinforcement learning. And this library exploits a nested parallelism in array. What is nested parallelism? Is the ability of a remote, say, task to invoke another remote task. Right? So it is recursive invocation across remote tasks or functions and methods. Right? So this, for example, if you want to evaluate a policy, that policy will call multiple rollouts to happen in parallel, and every rollout at every step may call a simulator, and the simulator also can be executed in parallel. Okay? It's integrated with these deep learning frameworks like PyTorch and obviously TensorFlow, and already supports a large number of algorithms, PPO, H3C, and so forth. And some of the parallel algorithms like Apex and others. RISELab is integrated with Tune, which is the other library. And this is a library for distributed hyperparameter tuning. Basically run in parallel multiple experiments on different configurations, is framework agnostic, and is resource aware. So you can run on a multitude of GPUs, TPUs, and obviously CPUs. And the goal of Tune is to do that efficiently to get you a good set of parameters for your model as fast as possible, and implement some multiple tuning algorithms, and this list is actually growing pretty fast, including population-based training, hyperband, and Bayesian optimization. It's easy to extend and use. It has a simple logging interface, provides checkpoint and fault tolerance, and it's a simple API you can plug in new tuning algorithms. Okay? It's growing adoption, and we are happy to see that. It is used, it's SageMaker, Amazon AWS. It's one of the reinforcement learning libraries you can use on Amazon SageMaker, and a bunch of companies are using it in production. So next, to just illustrate about one use case, I'm going to talk about online machine learning application on top of Ray. Unfortunately, it's deployed at one of the largest fintech companies in the world. I cannot give you the name, but the application is to provide the in-app promotion. So when you go on the landing page of that, the service provided by this financial service company, is going to provide you some promotion of some product of their partners, and then it's like I didn't mention, but it's deployed in production, and it was actually supported during one of the largest shopping days in the world. So obviously here is just, this is something very basic here. What this application has to do is to take the user logs. It needs to do featureizations and train a model and serve the model, which is going to make prediction inferences, recommendations about what to show on your landing page. And obviously, you want this to be targeted, personalized, and so forth. Okay? So one key question, and what this particular company struggles, is that, how fast you can go from the logs to train new models and to deploy them in production, right? And whether that matters, right? Initially, they started with a model being updated every day. Then later, they, using the state-of-the-art frameworks today, they went from 1 day to 1 hour. And by doing so, they improved the click-through rate by 5%. This is huge improvement. Click-through rate basically is one of the main metrics for this kind of application, is that the percentage of times you are going to click on that ad from the total number of times you've seen that ad impressions, right? So obviously they want to go lower, and to do that, they use Ray, and they go all the way down to 5 minutes, okay? And in doing so, they increase this click-through rate by another 1%, okay? Very happy, and how do they do that? They have kind of a custom streaming based on top of Ray, which then push the data to an in-memory storage, which is provided by Ray, and from here, there is a training, parallel data training system they implemented using TensorFlow with parameter server, and then the model they pushed to production using model serving. Again, kind of running on Ray. And this end-to-end takes just 5 minutes. Okay, so from the data to deploying it in production. Okay, so this is just an example. So this was about Ray. Next time I'm going to talk about Helen, another system we work in RISELab. And this is actually another, for this company I mentioned about, another use case is fraud detection. It's a financial company. And one particular use case in the fraud detection is money laundering, okay? So money laundering, obviously bank wants to detect these activities. The problem is that it's hard to detect. Now, what is the money laundering? How do you detect it? Actually, if you have the entire transaction graph, a money laundering activity is detected by detecting a cycle in that transaction graph. The problem is that, the criminals, when they do money laundering, they are going to use different banks, okay? So all this transaction graph is kind of split, right? So now, a bank can, in order to detect this kind of money laundering activities, may get this data one way, obviously we'll see this cannot happen. If you can get the data from all the other banks, then you can run your algorithms to detect the cycles, and you can flag possible money laundering activities. Obviously, this is not possible. Because competitors, these banks are competitors, they don't want to share the data, and actually, even if they want to share the data, they cannot do it because regulatory constraints. Okay? So really what you want here is to have some way to compute a model among these competitors, and from which all of them will benefit. So really here you have one of these instances which you want multiple competitors want to cooperate. And we call this kind of learning a model co-petition, right? And the co-petition is a neologism, and basically it says exactly what I mentioned earlier, is basically collaboration between business competitors in the hope of mutually beneficial results. Okay? And to do so, we build a system called Helen. It's a cooperative learning platform for linear models via cryptography. And basically think about this sharing without seeing and building a model. Okay, so Helen is based on MPC, Secure Multi-Party Computation. It's a decentralized protocol, and I'm not going to go into details. And we use an alternative training algorithm, ADMM, which has fewer iterations and can work over summary of data, so it don't scale linearly with the amount of data you are going to train over. And it has strong security properties. For instance, the attackers can violate the protocol, and it guarantees that even if all the other parties are compromised, my data is still safe, is still confidential. So strong properties here. And it's a quick evaluation. It's a song prediction data set from UCI, University of California, Irvine, 90 features. And the setup here, we have 4 parties, which are basically 4 instances in Amazon EC2, 2 in Oregon, and 2 in Northern Virginia. And the baseline, we use a stochastic gradient descent with a SpeedZ, which is one of the state-of-the-art implementations of secure multi-party computation. And here are some results. On the x-axis, the number of samples, the data set, the size of the data sets, and the time it's on the y-axis. You notice that it's a log scale on the y-axis. And this is the baseline. And some we say estimated because you couldn't go all the way because it's 10⁻⁷ hours. Okay? So it takes quite a bit of time. And this is our Helen. So it's over 900 better. So in this particular case, you can train, in what? A little bit more, less than 10,000 seconds. Seconds, which means few hours, right? So it's perfectly doable. Again, with the other one, you need, maybe 100, what? It's 100, more than 100 days. Okay? So that's it. So this is the second system. So again, we have Ray to support end-to-end machine learning AI applications, and Helen to provide you, which provides you the ability for now to build linear models and train them on confidential data from multiple parties. This again, for now, is linear models. Obviously, we are looking to support more complex models. The second part of the talk is about some application of machine learning to systems. Okay? And let me, before starting presenting these examples, these projects, let me start with make a note. I call here, classical deep learning and reinforcement learning applications. You heard, it's a Turing Award recognizing the progress in this area. Most of the applications which are highly successful so far are, like speech recognition, video recognition, language translation, are human tasks. And for this task, 100% accuracy is not expected because ourselves, we are not 100% accurate. Okay? So it's more like soft task. However, if you look at some of the system problems, you need to ensure correctness and explainability, and not only system problems. Here are a few examples. If you do program synthesis, if you generate a program, you expect that program to be correct, right? Robotic surgery of the same, you don't want errors there. And even mortgage decision, I said here, in these systems, beside correctness, you also want explainability, and this is an example of explainability. For mortgage decision, if someone denies you a mortgage, you can ask why is that, and they should prove you that the reason they denied you, it doesn't use any kind of discriminatory features. Okay? This is by law. Okay? So that's why for those mortgage decision, people do not use deep learning, for instance. Okay? So still, how you can use these machine learning techniques for this kind of problems? There are 2 ways to do it. And, at the high level. One uses for optimization. With optimization, you start with an artifact, which is correct, like a correct program, and you apply a bunch of transformations which maintains the correctness of the program, but at the end of after you are done with applying this transformation, you end up with a program which is faster, maybe more memory efficient, and things like that. The second one is to synthesize a set of rules or programs, okay, instead of doing it end-to-end. And I'll give an example later. And what is this good for? Because if you have a program or a set of rules, it's not always, but in general, you have a better chance to prove that it's correct or not, and it's explainable. If you have a set of rules, those are much more explainable than a deep neural network. Okay? So next I'm going to give these 3 examples, and they are going to fall in one of these or the other categories. So the first one is deep query, and this is about optimizing the order of database joins. This is database 101. Allow me 1 minute to go through it. So basically, it's this example to illustrate the problem. We have 3 tables, employer IDs, salaries, and tax tables, so three tables. And you want, say, for instance, in this case, to calculate the tax owned by employees of manager 1. Almost, everyone knows that this can be done easily by executing a SQL query like this one, which is going to join all these tables in order to get the salary, the location, and the tax for each of the manager employees. Okay? Now, if you look at, again, like this query, the most expensive part of executing this query is this join, right? Joining these tables. And the key question here is in what order you are going to join these tables. Actually, joining operation is commutative and associative, so you can do in kind of any order. And therefore, for instance, here are 2 examples in which first I join on the left-hand side. You are going to, on the right-hand side, first you join the employee and salary table, and then the tax table. On the left-hand side, you first, well, the other way from your side, sorry. You join the salary and tax tables, and then the employee table. And why do you care? Well, we care because depending on the order of joins, you can get very different performance. So in this particular case, the cost is at basically thinking roughly how long it takes to execute. In one case, can be 10x more than the other case. And the problem is difficult because you have exponential number of queries in the number of tables you want to join. Okay, that's difficult. And it's a lot of research on that in database literature, as you can imagine. It's an expensive operation, and it's hard. So you have a lot of heuristics, left deep, right deep, and many, many others. So the question you ask here is that can machine learning replace these heuristics with some efficient and data-driven strategy? And this is deep query. And our project, and this is build join plans with deep reinforcement learning. Obviously, you may ask here why reinforcement learning, right? This is another nail for the reinforcement learning hammer. It turns out that in this case, actually, it's a very nice natural formulation because a state is a set of tables which are joined so far. The action is what table you are going to join next, and the reward is a minus a cost, right? The reward has to a higher reward is better, so it should be the minus a cost. And we use, a pretty basic deep Q-learning algorithm. And here what happens is that the way you do it, initially, you start with 2 tables. You just pick 2 tables from the number of tables you have. And the state, it's a string of bits. The size of the string is the number of tables you want to join. Initially, and a bit, it's associated to 1 table. And if it's 0, means that the table has not been joined yet. If it's 1, it was joined. So in this particular case, we pick T0 and T4. So therefore, we are going to flip the state bits from the first bit T0 and the 5th bit to 1. Okay? And then the next action is basically pick the next table. And you go that basically recursively until all the bits are set, means you join all the table. The reward is again the minus cost. Okay? Now, one question is how you estimate the cost. It's a hard problem, and we are still working on it. But right now, what we do, it's you just observe a naive optimizer. So you have a database, it's doing its own optimization, and you observe the cost of different joins. And one problem with reinforcement learning is that it requires a large number of samples. However, a nice property of this problem is that if you run a join until completion, you get a lot of data which is useful to learn because each of these intermediate joins provide you useful information so you can use as a sample. So you run once, you get many samples. That's what basically say. And then you fine tune on real execution. This has some deep queries. It has nice properties. It generalizes to unseen queries. It's adapt to workload and hardware characteristics. If the hardware changes, the workload changes, the cost will change, and you are going to learn and adapt the way you are going to build these joins, planning, the joint planning. And it's efficient. The planning is quite efficient, as you'll see. So here it's a very simple example. You have 113 queries on a real IMDb data set and 21 tables. And for these 7, we are looking to join between 4 and 17 tables. The average is a relation per query. And we have 2 cost models. One is basically when, the cost model when the database, the naive query optimizer uses indexes. A more complex one is hybrid hash, in which actually, if the data doesn't fit in memory, it can spill over disk. And this is to see how robust are these algorithms to different cost models. And here it's one result. It's for cost model 1, index mostly. So here on the right-hand side, you have deep queries. And the way to read this is that on the y-axis, it's with respect, you have a number is how optimal it is with respect to the optimal join. And in this case, you do as much as possible exhaustive search to identify what is the optimal. And so therefore, ideally, it's 1. Everything should be greater than 1. And DQ is 132. And as you see, you have 2 actually, left deep and zigzag here, which are a little bit better. The reason they are a little bit better because they are exploiting the indexes, which deep query doesn't do it for now, and a few others which are much worse. Now, if you change the cost model to hybrid hash, again, this is a more complex model. Actually, deep query performs the best in this case. And also, you are going to see that in some cases, like write deep, now it performs well, while in the previous case, performs very badly. Right? So here, what you need to look is not only for a particular workload, which is the best, but you have to look about which is the best across multiple workloads. And from this perspective, deep query is doing very well because it's quite robust, performing very well on a variety of cost models. Right? This will become more and more relevant because right now you are deploying the database when you are running the queries. You are not running on your own walled server. You are running in the cloud on a different number of nodes and so forth. You are going to share some instances with other users, and this will create a much more complex cost models which are going to change over time. Okay. How fast is the time to optimize? So this is the plot showing that. So optimization latency, it's in milliseconds. Again, on the y-axis, you have a log scale. On the x-axis, you have the join size from up to 17. And as you can see, there are 2 regimes. In one regime, for relatively smaller join sizes, actually, deep query is not the best. There are a few of them which are better. But if you look about the numbers, this is around 10 milliseconds, right? So everything is a little, 10, 15 milliseconds or lower. So these are low numbers for interactive queries and so forth, so it don't really matter whether you have 5 milliseconds or 10 milliseconds, at least for interactive query workloads. And when you have large, number of tables you join, DQ is doing much better. Actually, it's the best. It's between 10x and several order of magnitude faster than the other state-of-the-art heuristics. Okay? So running time is very good and is very robust so far. The next project I'm going to talk about is NeuroCuts. This is a very different area. This is packet classification. Okay? So what is this problem about? Everyone in networking knows this problem. It's a fundamental problem. And what is this problem about is like you have a router or a firewall. You get packets, and you need to classify them. And you classify them based on the rule database. And this rule and this flow classification, the way it's doing classification, it's matching the field in the packet header, which is source address, destination address, source port number, and destination port number, and protocol type, to these classes, right? And these classes tells what to do with the packet. You may drop the packet, you may treat the packet with a higher priority, you may route it on a different path, or you may send it to an intrusion detection box, right? This is what you do. And these rule databases are pretty large. Sometimes there are more than 100,000 rules, okay? So this problem is similar to the point location problem in a multidimensional space. That's what it is. You can see here I have 2 dimensions. Each area represents a rule. And a packet here is a point. So you basically want to know whether the point is contained in one of these rectangles, which corresponds to a class. Unfortunately, this problem has some hard time-space trade-offs. If n is the number of rules, is d is the number of attributes, you can do optimally either, if you want log n time, classification time, or n is the number of rules, then you need a lot of memory. It's n power d. If you want very good space, so linear in terms of the number of rules, O n, the complexity is log power d, log n power d. None of these are practical because you want to classify this as a line speed, right, in microseconds. Actually, also, this is a little bit harder problem because here the classes can overlap and they have prioritization. You need to match all the classes and then figure out what is the priority which you are going to perform an action on the packet according to the highest priority class. Again, here there are more than 20 years of research. You have hardware solution. TCAM stands for ternary content addressable memories. They are power hungry and they cannot, it's prohibitive for large classifiers, and a lot of software solutions, starting with multidimensional decision trees, which are basically, think about KD trees, and many heuristics, okay? And all these heuristics build this kind of decision tree classification trees. Now, again, like think about here, there are 2 approaches here. One is end-to-end solution. You get the packet header, you have a great neural network, and it's going to spit out the classes to which the packet matches. That's one. The bigger one problem with this one is, again, you are not guaranteed 100% accuracy. And if you use this classifier for a security application, that's not acceptable. So instead, what we do, we synthesize this classification tree, right? And then we use this classification tree, which we synthesized to do the classification, like today. Another big advantage here is that you can use and you can provide this classification tree to today routers and firewalls. No change is required, because this will happen offline, building this classification tree even today, okay? So this is what the method we are using. Again, we are using reinforcement learning. Why reinforcement learning here? Is because it's, again, we can easily solve the problem of the high sampling inefficiency, because we can synthetically generate the traces of packets, and based on that we can compute, synthesize the classification tree. It's a naive Markov decision process formulation we use. I'm not here, it's a PPO, proximal policy optimization technique. And it's, again, the state here, it's like we are doing similar with which is the case of the deep queries. We are starting with one node. Here it's basically a class which covers all the packets, and then you are going to divide that, you are going to split that node recursively until you are going to get with a tree, which is hopefully efficient, both in times and space. The reward here is a minus depth of the tree. You want small trees, right? Because the size, the depth of the tree determines the classification time. And you want also, in terms of memory size, you want to have small memory size, because in these routers, you do not have lots of memory, because you need very, very fast memory. Right? These are the results. Again, I'm not going to go too much, just to give you a sense about the results. It's a ClassBench. It's an industry standard benchmark. And it's NeuroCAD, so it's a few other state-of-the-art classification heuristics. And you see you have for different workloads, for different in this benchmark, on the x-axis, the last number represents the number of rules. So you see up to 100,000 rules. And on the left-hand side, you cannot see it. Oh, you can see it. It's a microsecond, how long it takes. And here it's, again, the median, our NeuroCADs, it's 18% faster classification times than the state-of-the-art. And again, here, these are hand-tuned classification trees. People try really hard to optimize them. So this was time. In space, we are doing quite well, actually even better in terms of space, if you want to optimize for space. And the other kind of summary results here, so again, here on the y-axis, you have the bytes which are required by the tree. If you take any other state-of-the-art algorithms and we compare with NeuroCADs is at least 3x better on one of the dimensions, either classification time or memory. Okay? Great. So now, finally, the last project. I hope this will be a fun project, so will help with the energy in the room. It's Autopandas. It's, again, different problem. What is the problem here? You heard about the API economy, right? What we are witnessing is an explosion of the APIs. You know, I was talking with the faculty at Berkeley, said, with doing software engineering class, they say, well, you know, now every program, every application, you just call a bunch of APIs, you are done. Okay? Now, the problem is that you need to know what APIs to call, right? And what do you do when you don't know? StackOverflow, right? You ask a question, and you hope for an answer. So this is a question. It's from StackOverflow. You say, hey, how I turn that table up, you know, or data frame up in the data frame, which is, you know, the second one, in pandas, right? And you start to get answers. Some of them will be an efficient solution. In this particular case, you get an answer which is correct answer 4 days later, right? So what we want here is to have StackOverflow for APIs via program synthesis. That's the goal here. And we start with pandas, which is data frame transformation. It's one of the library of choice for data scientists today. And as you see in this plot, is a percentage of StackOverflow questions about pandas over the years. Right? So it's, you know, people really, really have questions here about pandas. And this is, I think, just a part of all the APIs. Okay? That's what you have to deal with. And if you look only one single function, so there is one single function, and you look how many single function and how many possible arguments you have, you know, the space is like 10 power 17. Okay? Huge space. It's for one function. So how do you do this? You know, there are a lot of work on programming by examples, and this fits that pattern. So basically, this is, you know, Autopandas. And you generate a program, random program. You execute the program, right? Input, see the output. If you match, you say declare success. If not, continue, right? Obviously, and you can do this randomly and so forth. Now, obviously, the question, how you are going to generate that program in an efficient way. I mean, to explore the search space in an efficiently, right? So the key here it's again, if you are just, by the way, how we generate the programs. For generating the program, we use graph neural networks. We encode the input as a graph using a graph-based encoding. What you see there on the left-hand side and right-hand side, you see each of these represents the shapes of the inputs and the output. And the arrows which connect them represent when you have the same value in a cell from the input and the cell from output. It's something very simple, right? Because you try to capture some of the correlation between the input and the output, and then you use a graph neural network. It's published ICLR 2018 by Alamanis and all, and that's fine. The problem is that, again, you need to deal with this huge search space. So how do you do it? The key observation here is, well, the simple answer, you use domain knowledge, okay? So what we do, we write these generators, which basically tells you how to generate the arguments of different functions. And here is an example again, it describes the space, and you can write this in Python. And here it's an example. Like for drop, you want to drop, you can drop a row or a column. So basically, here, the first argument will tell you whether you are going to operate on a column or a row. And then you are going to capture that when you are going to generate the function. And at least this is going to allow you to avoid some infeasible function construction. Like for instance, if I have 0 in the first argument here, then if I have 1 in the first argument, then it should be a row. If I have 0, it should be a column, right? So I'm not going to have 0 and have a row, okay? And then, so this will describe the feasible search space. And then, so this is domain experts, right? You write the generators. And then, what you use now, for each of these arguments, you have multiple choices. So this is what you are going to implement with your neural network. So the neural network is going to give you a choice of arguments in this constrained search space, right? Which is constrained by the generators, which are built by experts. And by doing so, in this case, for one function, we reduce the search space by 10 power 14 from 1017 to 10 power 5, roughly speaking. Okay? So, and here is this is preliminary work. Okay, so take with a grain of salt. So how do we evaluate? We evaluate on 70 benchmarks from, we look at some code snippets from StackOverflow. This is Python for a data analysis book and some videos from Data School. We have 70 such benchmarks. And we look at up to 3 functions. And by the way, if you look at the code snippets on StackOverflow for pandas, around 95% of them are 3 or less functions. So you cover a big fraction of these code snippets. So in this plot, you have for each number of functions, so it's basically a solution. It's 1 function, 2 functions, or 3 functions, and you have top 1 and top 5. Okay? And you can see the top 5 for 1 function is 94%, then for 2, 73%, and for 3, 60%, which at least we are pretty happy with. At least we started very, very low. Now, these are lower bounds, because this is what we are trying. We are trying, when we do this, we have to match the solution, which we find in Stack Overflow or this Python for data analysis book and so forth. Actually, for each of these, you can have multiple valid answers, right? So we don't look at that. We look to be the same answer, because it's like, and also here I have to confess, we cannot verify the correctness of the program. We rely on the programmer, on the user, to look at the code and say, oh, this is good. This is doing what I want, okay? Because, from a few examples, you cannot generalize. And in most cases, you have only 1 example, okay? But we believe this is a good trade-off and a good approach because if I give you the solution, it's much easier to verify and convince you that it's a good solution for your problem if you then compared with you don't have a solution in the first place, okay? So actually, this is my next to last slide. So in summary, at RISELab, we develop open source platforms, tools and algorithms for real-time intelligent decisions that are secure and explainable. During this talk, I went through a few projects in the intersection between systems and machine learning. And I think I'm very excited about this area. Because of these trends, you see more AI applications, and these applications are more and more distributed. You see this kind of new requirements like learning and developing models on confidential data. And also, we see more and more application which requires decisions which guarantee correctness and are explainable. Thank you.
Thank you, Jan. So there are 3 microphones in the 3 aisles. I remind you every time so that you can go up there and ask questions. Please, sir.
So for your Helen project, can you extend it to untrusted nodes, like a decentralized blockchain, that kind of stuff? And if you do, can you prevent those nodes to actually decipher the model, just like MPC type of?
Yeah. So there are 2 questions there. So the Helen actually has strong properties. So if a node is compromised, it's not going to compromise the confidentiality of your data. So you address that problem. The other one is about the model. Actually, this is also the model to stop you to learn. That's very hard because you can still learn the model, right? Because the one way I can do it, I don't do anything. So I'm just participating with the protocol, like you provide my data and so forth, and I'm just snooping. And I'm going to see eventually, the model that is for my data.
So you probably expect this question. Is Autopandas going to be available for...
Which one?
Is Autopandas going to be available for use soon?
We hope so, yes. Absolutely.
It sounds like fun.
Yes, we hope so.
Let's thank Jan one more time. Thank you, Jan.